All right. Hello and welcome to the Foam Community Call. We're here today talking about dynamic proof relocation, and more specifically to highlight some of the work we've done testing out LoRa radios as potential zone anchors, as well as the simulations of the time sync protocol. So I'm here with my colleague and lead engineer at Foam, Ilya. So hi Ilya, thanks for joining.
Hi everybody.
Okay. So let's just get started, and first let's talk about what are these LoRa boards that we've been using, and what makes them so interesting and special, and how can they potentially work as a zone anchor. So if you maybe explain to me what I'm actually looking at here.
So this is what's called some people call it an evaluation board, other people call it like a discovery board. That's actually the official brand name of them. So what these are very low, it's a very low cost microcontroller, very low power, like on the order of $2 or $3 a pop. And generally the idea with these is like you would use them to develop against a certain chip to see how it works, learn a bit more about it, and possibly prototypes the product. So the neat thing about this particular board is that it also has an embedded LoRa radio on it, which is great because you can pick this thing up for about $25-30 and just start playing with LoRa. So what's really special about these is they're running a certain firmware which demonstrates that really tiny, cheap, readily available boards like this can be used for really high precision timing of the data that comes over radio. So one of people's concerns about LoRa specifically was that, okay, it's low power, but it's really long range, but it's really hard to get accurate timing info with it. And what we've actually been able to demonstrate, in fact, with these two specific boards, is you can get some insanely precise timing out of them. So we actually have the firmware that's currently running on these just sends a demo packet. It sends a train of 100 little -7 packets followed by just, hey, I'm a radio. And it logs the timing information that was associated with it.
And what's a -7 packet?
-7 is just it's a way of encoding data to MAC layer, specifically so multiple radios don't talk over each other. It's kind of like if you think of Ethernet, you have a whole bunch of things plugged into the same Ethernet hub. They can't really talk over each other. This is like 90s tech right here. Now we have switches where it's not a problem, but with radio, of course, it's a bit more free-for-all, so to speak.
Okay.
So it's just a way of encoding data to make sure that other people don't talk over each other.
So we have these standard developer boards, and it's one running a custom firmware, but we also had to add a certain part to it to be able to run this experiment. Maybe we can talk about
that part is also dirt cheap. What it is it's just a little oscillator, and oops, I unplugged it just so we can get a better view. And all it is a tiny little crystal right here held together with if you focus, just a little red wire. And all this does is this just feeds the internal clock on the chip itself, and we just use that to run a counter, and that's actually how we're able to get the timing info out. So what we could do is we can actually just demonstrate this working right now.
Yeah, let's go to that.
Where, just take a sec to set up.
So here we're going to just replicate the time sync protocol in this basic firmware where they're just sending simple messages, but we're able to get a large dump of those time data. And once you go to analyze them, you can do some linear regression and get up to about 2 nanosecond precision. So that's what we had put in our previous update. So for this call, we want to just basically show what that experiment actually looks like in the lab.
Yep, so we have two boards here. We have heard of before, the infamous blue button. And what this is just going to do is as soon as you hit that blue button, one of these radios is going to start sending a bunch of data over the air to the other one, and the other one is going to log the internal timing counter. That's as each part of the data packet is received. And as soon as we hit this, we're going to see a whole bunch of lines. It's 100 lines, each of them with the value of a counter. Now I'm not going to plug this in right in front of you because it takes a teensy bit to do it by hand. But what you would basically do is you would take these timestamps here, and in this, let me zoom in a bit, this lovely little Excel spreadsheet, which by virtue of being Excel is tedious. Basically, you just plug that right into this column here, and what it'll do is it'll calculate a regression, and as you can see, the variance is nearly non-existent. So you have pretty consistent timing intervals across each part of the packet received, which lets you know you're getting very precise data out. Now, naturally, in the real world, you're not plugging in each of these things by hand. You're just having software do this for you, and, well, that's the easy part.
Foam is building a decentralized proof of location protocol that offers a higher level of security and network strength than conventional location-based services.
Okay, so basically we've just very quickly highlighted some of the findings from this experiment that shows that you can actually use these Allura boards to get that level of precision. So that's a great kind of validation that you can use consumer level hardware. And where we're at now is taking that firmware and allowed to do more sophisticated things. So right now it can only really send these time messages back and forth at a really high precision and log them. So separately, we've been developing and testing out a Byzantine fault-tolerant time synchronization protocol, and that protocol is radio agnostic. So right now, when we're testing it, we're running basically simulations and adding nodes on the computer, and ultimately that kind of data is then being stored on a Tendermint blockchain so that these radios actually share the state machine, and that's kind of the work we've been doing now. And the main kind of bridge is how do we then have the updated firmware to take this software and run it on the radios. So that's really going to be the next major step. But maybe Ilya, you can just speak to what this actual protocol is you've been working on, what language it's written in, and what it actually is doing.
Okay, so this is an implementation of a Byzantine fault-tolerant time synchronization protocol. So far, this is the rough version of it, meaning rather than one clock tick synchrony, it's within a allowable range. So what this does is it actually simulates a bunch of individual nodes with radio links between them, and because it's a little bit stochastic right now, you might see like sometimes time syncs of like 1 or 2 clock ticks. I just ran it, it was about 21. So there's some refinements to the simulation as well to be made, but it's a general indicator of whether the protocol actually works. It's very promising. More than just promising, it's already demonstrated that it's working, which is pretty cool because these start up at slightly different times.
And so what language are you working in?
So this is written in Go, just because Go's threading model, or rather Go routine model, is very... It translates very closely to how this would be done in hardware as well, where you kind of just set up routines that just run little bits of code. They just sort of barely communicate with each other, but not like, crazy enterprise grade like threading and so forth. We should actually redo that. That was terrible. Cut.
Okay, so the protocol is written in Go in the simulations, and then as it's running, how does it actually interact with the consensus engine, in this case Tendermint?
So in this particular demo, which I'm going to start again because it looks really cool as background, in this particular setup, it actually doesn't matter. The time sync protocol itself is radio agnostic. It doesn't matter for the protocol itself whether it's being written to a blockchain or not. The blockchain is just there for other people to say, hey, are these guys actually running the protocol or saying they are? So in this particular case, we're actually synced down to 16 clock ticks, which is pretty cool. That's a good start to get down to 1. But basically, each of these columns is an individual node, and they can be wired into a blockchain just reporting where they are in the time sync protocol. Mm-hmm. And from that point on one hand, they're running the time sync protocol. They're synchronized. They're logging what messages they're seeing from other people, which kind of keeps each actor honest by virtue of the other actors wanting them to be honest. and you just write that out to a blockchain for verifiers to then watch, hey, is this zone behaving like it should?
So right now you're running the simulation on one machine, so that's 4 threads simulating 4 nodes?
5 threads simulating 5
5
nodes.
nodes, okay. And so...
It's actually, there's 4 threads per node since the way the algorithm works, but that's technical details.
and so one of the things we're going to be doing next is moving this off the machine and setting up a kind of Raspberry Pi setup to kind of simulate more real-world latency of light speed, and instead of having all the simulations running on the same computer, actually start to separate them from different wires. And so I'll let you say more about that in a second, but really what that speaks to about our development path is because the protocol is radio agnostic, we can keep developing it on, from a software point of view, test it on different hardware, run it over wired, so they're actually connected via wires, and eventually as the firmware is developed on the radios, you just flip out the wires and have that actually be a radio instead.
Yeah, so one of the things that we're currently putting together is what we call the GeoPickle, for reasons that we will not go into, but let's just say the boards look like pickles. And what it is it's actually a little rack-mountable setup of Raspberry Pis where you can make each Pi an individual one of these nodes that can be running the protocol, just in software over Ethernet. They can be running it over radio. They can be running it with, a potato battery as a communication link rather. And what that'll actually allow us to do is you can fit about 40 of these in about 5 rack units of space, which is enough for at least 10 zones of 4 zone anchors each. So then we could start testing things like continuous coverage of zones, like the total foam area. And it's just one of those really cool stepping stones, but you don't need like a crazy elaborate $20 million lab to do this stuff. You can do this at home, basically, which to me is one of the coolest parts of all this.
Well, thanks everyone for tuning in. We just wanted to give an update on how the experiments were going with the radios and where the software development is, and we'll be sure to follow up with more blog posts and updates in the weeks to come. Thanks.